Welcome everyone to the 6th lecture of this Advanced Topics in Quantum Mechanics course. Today, the focus of the lecture is going to be, well, we're going to start with the concept of erasure, which is a connection between information theory and thermodynamics, specifically that when we process information in the form of bits or whatever form it is, they actually entails a thermodynamic cost, either in the form of heat dissipated into a hot bath or work that we have to provide. Also vice versa. If we have information about a system, we can use that information to extract work from a hot bath or from any other system. And then as we go through the lecture, we will understand that erasure is essentially one facet of a class of thermodynamic operations that includes cooling and work extraction. In the case of erasure and cooling, we use a source of work to gain information about a system or to put a system into a state of less entropy than it had originally. Whereas in the opposite case, in case of work extraction, we use the fact that we have information about a system, that is, it is in a state of lower entropy than it could be, to extract work while increasing its entropy or while taking it closer to thermal equilibrium with a bath. First, we will understand this from the perspective of a paradox and the historical argument as to why these two things are connected. We will derive a form of the second law that captures the connection and the bounds to what we can do. And then we will go into an explicit protocol that does these various operations, erasure, cooling, as well as work extraction. That's due to Paul Skripczyk, which is a sort of quantum version of a quasi-static reversible thermodynamic process. Okay. Let's begin. Right. So what we start off with is Maxwell's demon, which was a thought experiment introduced by the famous physicist Maxwell. And it's a very simple experiment. Imagine that you have a box with a divider in the middle, and that divider has a little opening which can be opened and closed in order to allow particles to and from either side of the box. And at first you start with the gas in the box just being in thermal equilibrium with some temperature T. So of course, being in thermal equilibrium doesn't mean that all of the particles in the box have the same velocity. It means that the distribution of velocities looks like the Maxwell-Gibbs distribution that we're used to already and we've discussed. So now imagine that there's a little demon that sits here. And I apologize for my very rudimentary drawing skills. And the demon does the following. The demon looks at every particle that approaches this little partition in the middle of the box. And if the particle is one that is moving faster than a certain velocity, the demon allows it to move from the left to the right of the box, but not from the right to the left, so only in one direction. If the particle is moving slower than that particular velocity, the demon allows the particle to go from the right to the left of the box, but not the other way around. So you start with something that is equilibrated on both sides of the box the same way, but you can see that if the demon keeps repeating this process, you're going to end up with the faster particles on the right of the box and the slower particles on the left. So you're going to have a hotter temperature in the right of the box compared to the left of the box. Now, this is clearly an apparent violation of the second law of thermodynamics, because what we've started with is a single temperature, and we've ended up with two different temperatures. It's the equivalent of taking a container of water and separating it out into a container of ice and a container of steam. So Maxwell's argument was that you should be able to do this. A demon should be able to look at this and violate the second law of thermodynamics. Half a century after Maxwell, a physicist named Szilard came up with a simplified version of this experiment that allows us to make a quantitative connection. So the Syllab Engine, as it's called, I think this is with two accents, hope I haven't got it wrong, is the following. So imagine now the same box. And in it, you have just a single particle. Let's assume that it is well, the particle is either in the left or the right of the box, and you have a partition in the center of the box, But this partition can be connected to, it's essentially like a piston. It can be connected to a weight. And what this allows us to do is it allows us to transform the internal energy of the particle inside the box into potential energy of the weight. So for instance, imagine that we still had our demon as before, and the demon realizes that the particle is at the left of the box. So we know the particle is at the left of the box and not at the right of the box. Now I do the following. We tune the weight in such a way that, and the piston, in such a way that the particle is allowed to expand, is allowed to push the piston quasi-statically and reversibly from the middle of the box to the right side of the box. So we go from this quasi-statically to this state. Oops, sorry. Where this is now, sorry, I drew it the other way around. I want to do work, not use up work. I have the particle is in the right side of the box, and it's allowed to push the piston in the other way so that we end up with this. And the weight has gone upwards. So what we've done is we've raised the height of the weight. So that's an increase in potential energy. We've converted internal energy of the particle into potential energy of the weight. And in doing so, we now no longer know the precise location of the particle. Before we knew it was on the right side of the box. Now it's somewhere inside the whole entirety of the box. Note that if I found that the particle was on the left, I could just reverse this and place the weight on the left and push the piston towards the right. So that where it was found doesn't really matter. And now if I ask, what is the work that I gain from this, assuming that it is a reversible and quasi-static process, and assuming that it's an ideal gas, I have that I can write this as the integral of the pressure over the volume from V initial to V final. Given that's an ideal gas, I can write this as KT upon V, because I know PV is equal to KT. So this is PV dV by V. This gives us KT log V from V initial to V final, which is KT log of V final upon V initial. That is KT log 2, because the final volume is simply half of the initial volume. If this appears strange that we treat a single particle as an ideal gas, you can imagine that there were actually n particles on one side of the box, and you did it and you allowed all of that full gas to expand. All that you would end up with is a multiplication of n through all of these, because you'd have PV is equal to nkt, and then you would get nkt log 2 in the case of many particles. So what it appears to be is that, sorry, I forgot to add, this box is kept in thermal equilibrium with a bath at temperature T. So this is important. As the piston is moving, the particle itself is kept at thermal equilibrium to T. So this is not only reversible, but it is also isothermal. Okay, so W is equal to nkt log 2, and there are two ways of writing this. One is to say that this is equal to, nkt log 2 is equal to kt times delta S of the particle. So the increase in the entropy of the particle has been transformed into work. And another way of writing this is to say that this is equal to, so note that this is equal to K T delta S. This is, well, sorry, this is equal to delta Q of the thermal bath. So in other words, what we have managed to do is we have managed to use the one bit of information that the daemon has, that is which side of the box the particle is in order to extract an amount of work from the hot bath that is given by KT times delta S. So we have transformed heat into work, which is again a violation of the second law of thermodynamics, which should not have been possible. So we see clearly there's a link between information and thermodynamics. Having information allows us to extract work. Note that we could also do the converse and decrease the entropy. So for example, start with the particle anywhere in the box, place a piston on one side, and then use work to compress it into half of the box. And that decreases the entropy of the particle and gives us one bit of information. We know now the particle is on one side of the box. In order to do that, we'd have to do the inverse of this process and provide an amount of work that is exactly equal to KT times the change in entropy of the particle. Okay. Are there any questions at this point? No? Okay. So Maxwell's demon, the thought experiment, was in the 19th century. Szillard's engine was somewhere in the beginning of the 20th century. But half a century after that, or within the next half a century, many people, but specifically Landauer as well as Bennett, came up with an argument as to why there is no violation of the second law, in fact. And the reason is because the demon requires a memory to store the information. So we've just said, oh, the demon sees where the particle is on the left or the right, or what velocity it is, a higher velocity or lower velocity. But the physical process of this is that the demon must write this information onto the memory, onto some register within their physical composition. And then that memory changes in a manner during the computation. And what we see, in fact, is that that memory changes in a manner which has a thermodynamic cost. So let's do this in sort of the way a quantum circuit would go. So I can describe the particle in a box as in the state left, left, plus right, right, over 2. So this is a mixed state over the full box. And this is, let's call this a system. And this starts out tensored the state of my register, which I can say is in the state 0. It doesn't matter, I can just have it be in some fixed state psi. And then what I do is I do a measurement, which I can think of very similar to a C0 between the system and the measurement device. So this is the gate which takes L system 0 device to L0, but R system R system 0 of the memory to R1 of the memory. And so this goes now to the state L0, L0 plus R1 over 2. And this is a reversible transformation. Now, the point that was made by Bennett was that the next step where work is extracted is an operation that changes the system back from either being on the left or either being on the right, back to the fully mixed state that it had before. So we extract work, and this changes back to the system goes to identity S over 2, which by the way is the same as this one. So this is identity S over 2 tensored. And now we want to see what the state of the memory is. And the point is that the state of the memory now is, if we trace out the memory in this state here, this is row system memory, we see that row memory is in the mixed state 0, 0 plus 1, 1 over 2, which in fact is the identity over the memory over 2. It's maximally mixed state of the memory. So this now is identity of the memory over 2. So we start with the state of the memory being in 0. Because of the measurement, the memory gets correlated with the system. So it's either in 0 or 1, depending on whether the system is in the left or the right of the box. Then we use that information, the system being in the left or the right of the box, to extract work, returning the system alone, the reduced state of the system alone, back to its original state. which is the maximally mixed state, but the memory has been left now in the reduced state that it had at the end of the first operation, which is the measurement operation, and that is in the maximally mixed state 0, 0 plus 1, 1 over 2, which means that this memory can no longer be used to repeat the process again. If we wanted to once again extract more work or try and create a perpetual motion machine via the operation of this daemon, we would need a new memory, or we would need a larger dimensional memory so that we could keep making it more and more mixed. Now, this is a bit of a hand-waving argument because I haven't precisely argued that I cannot return the memory as well through this operation back to its original state. And the reason we cannot do that is because of the notion of reversibility. In order to argue this, I'm going to now do this in a much more abstract sense. I'm going to follow the reasoning from a paper by Reeb and Wolf, which is the following. So imagine now that I put this on a formal setting. I have a work storage system that is going to exchange energy. I have a reservoir R. So this is for work. This is a reservoir R. I have my system. And I have the daemon's memory M. And we start in some state rho W, tensor rho R, tensor rho system, tensor rho of the memory. And we do some unitary on this entire state, taking us to some final state of all of them, R, S, and M. And so we don't know the exact form of the final state of all four of them. It might be correlated, might not be, but what we do know is the following. So this,
sorry,
yes.
Can I ask a question? Why is work a state? Wouldn't it be unobservable?
Aha, no, it would be. So the reason I include work as a state is because when we do work, we always end up changing the state of a physical system. So work is stored in the state of a physical system, whether it is a state of a weight that we raise or we lower, or it is the internal energy of a fuel that we use or a battery. In real life, we always, well, not real life, but in physics, we always associate work with the change in internal energy of a system. That's where work is stored.
But in that case, we can also store work in the reservoir. So we could consider everything in the reservoir, right?
Aha. No, well, because what I'm doing here is by separating between W and R, what I'm doing is I'm separating the part which stores energy at zero entropic cost and the part that stores energy at maximal entropic cost. So R is always in thermal equilibrium. So delta S max by Jane's principle, whereas W, delta S is equal to 0. So I'm separating these two parts of the system. So it is true that you can also consider the creation of useful energy to be, for example, you take a bath and you put in energy into it, which is heat. And so you heat up a bath at a higher temperature than your environment temperature. But which is something actually that I will get to eventually as a generalization of a work source. Instead of considering the ideal work source as being delta S 0, you can consider delta S to be another quantity. But for this particular derivation, all that matters is that we separate out the reservoir that is at maximal entropic cost and the system that stores energy at zero entropic cost.
Okay, thank you very much.
Yeah. Right. Okay. So we continue. So in fact, I continued what I was just saying. Exactly as yes. So this U is energy preserving, and it has to be, because otherwise we will lose track of where the energy has gone. Actually, as a partial answer to the question that is just asked, I could consider without W, I could just consider rho R, rho S, rho M, and then consider unitary that's not energy preserving, which would have the same effect, because when I consider it to be a unitary, I say that the entropy does not change as a result of the operation. So considering a non-energy preserving unitary versus considering an energy preserving unitary and a specific work source that doesn't change in entropy, they are interchangeable. They will have essentially the same result in the derivation that I'm about to apply. Okay, so as a result of this, I'm now going to do the following from the definition of work and heat. I'm going to say that delta E, so I'm going to call delta EW as the work. I'm going to put an arrow to say that this is the work stored. So the work stored increases. I'm going to call delta E of the reservoir. This is equal to beta times, this we label as delta Q R. So this is the heat stored increases. Delta ES is delta EM, which is 0. So we associate the system and the machine with no Hamiltonians at all. So both of them are Hamiltonian less, so the energy less. Okay, so from the first law, just from energy preservation, we have that W up plus delta Q, or actually I should just call this Q instead of delta Q. Heat. QR up is equal to 0. So W up is equal to minus QR up, or I could also write this as plus QR down to denote heat that is extracted from the bath if I wish to exchange it to that. Okay, so that's the first law, so we just encode this. Now, what I'm going to do is the following. I'm going to talk about the subadditivity of entropy, which is the following. So imagine that I write the entropies S of the reduced states of the final the system plus S of R prime plus S of rho S prime plus S of rho M prime. So these are the sum of the final entropies of each of the individual reduced states of the work reservoir, the work storage system, the thermal reservoir, the system, and the memory. This is greater or equal to S of rho S R, WRSM prime. Now, this is just the subadditivity of entropy. This is a statement that holds both for quantum as well as classical states. If you look at the entropy of the marginals of a distribution or of a quantum state, and you add them together, you're always going to get something larger than the entropy of the joint state. But this entropy of the final joint state is actually equal to the sum of the entropies of the initial states, because I started with a state that was, remember, was a joint state. Was a product state. So the entropy of a product state is in fact just the sum of the individual entropies, which means that the entropy, actually I should add one more. This is S of rho WRSM. And the reason for this is unitarity does not change. A unitary operation does not change the entropy of the global state. And the initial state is a product state, so I can split the entropies this way, which means that now I can write delta S on this. There's a typo here. Because I take each of the initial entropies to the other side, so I get the change in entropies delta S on the work storage, plus delta S on the reservoir, plus delta S on the system, plus delta S on the memory is greater or equal to 0. Okay, this by assumption is equal to 0, because it's a work storage system. This, which is delta S of the reservoir, because it's if I treat it as an ideal reservoir, I'm going to get that this is equal to beta times Q of the reservoir. Delta S of the system, I'm going to place as 0, because the whole goal of the Szilard engine or of Maxwell's daemon is to observe where the system is, to use that information to extract work, and end up with the system in exactly the same state. So the system's final state, at least the reduced state of the system, is equal to the initial state of the initial reduced state of the system. Rho S prime is equal to rho S. And this one, we don't know. We would like to see what it is. So in the end, what I get is, if I put each of these in, I get beta times QR. This is, by the way, up, plus delta SM is greater or equal to 0, which means that beta QR, or let's put it this way, delta SM is greater or equal to beta QR down. So I just flipped the sign on QR. I put it on the other side, so the sign would flip, but I flipped it back by just associating the heat drawn from the bath instead of heat put into the bath. So this is very important. What I get is, if I try to do this process that the daemon tries, it starts with the system in a particular state, measures it, uses that information to extract work, returning the system to its original state. I get that the amount of heat that I've managed to extract from the bath and convert to work must be matched by an increase in entropy of the memory. And this is precisely why in the previous example, it could not be the case that I managed to return the memory back to its original state that it started off with, which was a pure state, because that would mean that the entropy of the memory did not change at all. So the entropy of the memory must change by an amount that is determined by the heat that I've converted into work. Which leads us to the following quandary. If I keep repeating this process, there's a limit to how much I can do this, because we know that this entropy of the memory is less or equal to, for example, log of D, where D is the dimension of the memory. So if I start with some finite amount of memory, then eventually the daemon is going to fail to do anything more, because it runs out of memory. It has a memory that's already in the maximally mixed state and cannot do anything more, which is exactly what we got in the example we just had here. The daemon was able to extract work via 1 bit of the memory, but in the end, the memory ended up in the maximally mixed state, and from here we cannot go further. We cannot extract any more work out of heat. Okay, so what's going to happen is that eventually we need to reset the memory, and this is what is called erasure. Taking the memory that is in a mixed state and returning it to a fixed pure state so that it can be used for the next process. And what happens when we try to reset the memory? Well, we can easily guess. We just apply the same process over again, but in the backwards direction, where we start with the memory and we extract work and seek to use that to decrease the entropy of the memory. And of course, we're going to get exactly the opposite. We're going to get that in order to erase the memory, to decrease its entropy by delta S, we must use an amount of heat that is at least, well, QR will be of the order of delta SM divided by beta, which is the temperature of the environment that we use in the protocol. And so what we've established here is that there is no violation of the second law due to Maxwell's daemon. And the reason is because the processing of information, which is the erasure of a memory to prepare it for a information processing task, actually has a thermodynamic cost. And when we include that cost, we have no violation of the second law of thermodynamics. Is there a question about this? None. Okay. So what I would like to emphasize here are the sort of ingredients that we used in order to get this statement, which are the following. So the first one was the ingredient of unitarity, or reversibility. So one of the assumptions I made in this protocol is that we do a unitary operation on the entirety of the work, the path, the system, and the memory. And what this implies is that physics is reversible. If we have any loss of information or anything that's irreversible, it is because on a local scale, when we deal with subsystems, we lose information or we lose correlations about some correlations between the subsystems. But the physics itself that is describing what happens to all of these systems together must always be unitary or reversible. If we were to take away this, then clearly there's not going to be conservation of information or the second law, because irreversible transformations already include the loss or gain of information in them. So the first ingredient is that physics on a global scale is unitary or reversible. The second ingredient that we had was that we started uncorrelated. So that was the assumption that my initial state I could write as a product between each of the work, the reservoir, the system, and the machine. And the reason again is simple. If I start with a correlated state, then clearly there is some information between the states that I can use in order to extract useful work or heat. And where we can, time permitting, discuss a quantum version of this based on entanglement that allows us to extract more work than we could classically when the correlations are high enough between the initial subsystems that are involved in the protocol. So that's the second thing that we have. The third ingredient is the sub-additivity of entropy, which is that when we have a global state and we look at the entropies of each of the subsystems and add them together, we're always going to get something that is larger than the entropy of the joint state. So whenever we forget the global state and we look only at the individual reduced states, typically we will lose a positive amount. Well, we always lose a positive amount of information in this process. So if we add up over the subsystems, delta S, we always get something that's greater or equal to 0. And this I would put to be the information theoretic base for all of the versions or all of the standard versions of the second law of thermodynamics. And the final ingredient is to associate heat with delta S maximum and work with delta S equal to 0. And this gives us sort of a thermodynamic version of the second law. In other words, on an information theoretic basis, all we have is the sub-additivity of entropy. But then when we associate some of these entropies with heat or with work, we end up with the thermodynamic version of the second law, which involves statements such as you cannot convert heat into work, or statements about the free energy, which we will come to next as well. Okay. Yes, is there any question so far? Nope. All right. In that case, I think even though this is still, this is half an hour into the lecture, I think let's take a 5-minute break and continue at 4:25, so 16:25 with the lecture. So I will continue with an explicit protocol for erasure next. See you in a few minutes. Let's consider now a protocol for erasure. So I want to do the following. I want to take a qubit that starts in a maximally mixed state, for example, and convert it into a pure state 0, 0. Okay. I could generalize this statement to say I want to convert a qubit from any mixed state to a pure state, which is what we will actually look at when we consider the full protocol. But for the start, imagine that I'm just doing this. So I'm allowed, so I have my system. no, sorry. This is now, we're considering erasure of a system. So this is really the memory we were considering before, the thing that we want to use in information theoretic tasks. So from now on, I'm just going to call it the system. There's no more memory. So this is my system that I want to erase from a mixed state to a pure state. Okay, so one way of doing this is to do the following. So I know that I have my system and I have my bath. And from the bath, I can pick any state of the form e to the minus beta times h upon z. That's the definition of an ideal thermal bath. For any Hamiltonian, I can pick the thermal state from that bath. And so what I could do is I could pick the state of a qubit from the bath. So I can pick a qubit of energy gap, let's say EB. And I know that this will be in the state, let me say, Q0 is equal to 1 upon 1 plus e to the minus beta EB. And this will be Q1 is equal to e to the minus beta EB upon 1 plus e to the minus beta EB. So I have these two states, so the system rho s tensor rho bath. And then what I do is I just do the swap unitary. So remember, the swap is just the flipping of the states 0, 1 to 1, 0, and the Hermitian conjugate. So these two states flip. And I end up with rho bath tensor rho system. And I'm abusing notation here slightly. Rho bath here refers to the original state of the bath, but here on the system, Hilbert space, and vice versa. So my system is now going to change to exactly this. So it's from half 0, 0 plus half 1, 1. The system is going to change to Q0, 0, 0 plus Q1, 1, 1. And so clearly, if I increase the value of EB, so note that if I fix the temperature of beta and I simply change the value of EB, this state on the bath is going to change. In particular, the ratio between the excited state and the ground state is just e to the minus beta EB, which is a number that becomes smaller as EB increases. So the larger that EB is, the closer this state of the bath is going to be, of the bath qubit is going to be just to the ground state. And this is the final state of the qubit of the system, meaning that I can cool or erase the qubit of the system arbitrarily close to the pure state 0 by simply increasing EB of the bath. However, what I should consider when I do this is the work cost of this operation. Because the change in energy of the system, so the change here, I've taken the system to be of 0 Hamiltonian, for example. So imagine that HS is equal to 0. So the system doesn't have a Hamiltonian, starts out in a maximally mixed state. But the qubit does have a Hamiltonian. The purpose of the Hamiltonian of the qubit is to be able to pick different populations by tuning the energy gap. So delta E, which is the work cost, is delta E of the bath. And this is going to be equal to half. So the final energy of the bath is going to be half times EB, because the final state of the bath is just the maximally mixed state, which is the initial state of the system. So rho prime of the bath is equal to rho of the system, which is half 0, 0 of the bath plus 1, 1 of the bath. So the final energy of the bath is half EB, and the initial energy of the bath is Q1 times EB, because that was the population in the excited state. Right. So this is, we can write it as half minus Q1 times EB. Now, limits as EB tends to infinity, which is the limit in which we get perfect erasure of W, is equal to half minus the limit of Q1 in this case is 0, but this becomes infinite. So this is just positive infinity, which means that the perfect erasure that we would like to do comes at the cost of, comes at diverging energy cost if we try and do it within a single swap operation. Is this explanation clear? Or the math of this clear? Okay. So what we would like to do now is to find a different protocol that actually does not diverge in the energy cost. And the way to do it is before I talk about the quantum manner of doing it, let's think about the Szilard engine. Because in the Szilard engine, erasure corresponded to, we had a piston where the particle that was covering the entire box, and we connected this piston to a weight, which would pull the piston and compress the particle. Now, the point is, if we connect this to a very heavy weight, it's not going to be a quasi-static operation. It's going to move too quickly. And we know then that we will, by the laws of thermodynamics, we will use up in general too much energy. In order to make this a reversible quasi-static transformation, the weight must be chosen to perfectly counteract the pressure provided by the particle, so that this goes only a small length delta L and remains in equilibrium with the particle. Then we increase the weight because the pressure of the particle will have increased, and it will move another delta L, and so on and so forth. So what we want to do is we want to split the entire operation into small bits, each of which is in quasi-static equilibrium or quasi-equilibrium with the thermal bath. So we do the same thing here. Instead of swapping the system, this is the system Hamiltonian, the state 0 and the state 1, with a thermal state of the bath of a very big Hamiltonian, instead we swap it with something that's very small, and then something that's slightly larger, and then something that's even bigger, so on and so forth, until something that is in fact very large. And why do we do this? We do this because, so imagine what happens in the first step. Here my rho S0, the initial state of the system, is just the maximum state of the system. And this, which I call B1, B2, B3, so on and so forth until Bn, the state rho B1, which is equal to e to the minus beta EB1. Oh, sorry, this is just, that's wrong. That's 1 upon 1 plus e to the minus EB1 times 0, 0 plus e to the minus beta EB1, 1, 1. When EB1 is very small, we can expand this to first order, and we get that this is 1 plus, and this is just going to be 2 minus beta, oh, sorry, that's beta EB1. This is just going to be 2 minus E beta EB1, but on the top it's going to be 0, 0 plus 1 minus beta EB1 times 1, 1. So this is a state that is in fact very close to the max minimic state. When EB1 goes to 0, we see this is the max minimic state. For EB1 being very small, this is something close to the max minimic state. In which case, the state of the bath that we are swapping with that of the system, those two states are actually very close. Once the state of the system becomes the same as the state of the first thermal qubit, then we swap it with the next thermal qubit, which has a bit of more energy gap. But in each step, because we have split it into a sequence of steps, we ensure that the state of the system does not change by a very large amount. Okay, so we have a sequence of these many n steps. And now what I'm going to do, in fact, is I could do this with the system having no Hamiltonian, but I would like to generalize this already to give you an idea of what we get. So I'm going to consider that my system actually has a Hamiltonian. So it starts out as, so we have ES. And we start with some P0. Oh, let me write this as P0 and 1 minus P0. So my system begins in some arbitrary state. And what I do in the first step is I pick a Hamiltonian from the bath. So my EB0, and I'm going to pick it such that it is slightly cold then the system. So P naught plus delta P, 1 minus P naught minus delta P. Now remember, I can always do this. Given any population that I want to have in the ground state and the temperature of the bath, I simply solve for the Gibbs ratio and choose an energy gap of the bath that corresponds to that population. What I do next is then I pick the next one, EB, let me call this EB1 actually. This is the first bath one. EB2 is P naught plus 2 delta P, 1 minus P naught minus 2 delta P, and so on and so forth until my last one is P final and 1 minus P final, and P final is equal to P naught plus N times delta P. So here I've made the population increase linearly in each step. Okay, right. So now in each step, what I do is a unitary between the system and the bath, N, and I keep track of the work cost, and I keep track of the entropy changes. And this unitary is just going to be the swap unitary. So I simply swap the system and the bath in each step. Okay, so let me look now at the change in entropy of the system under a single step. So delta ES from the state N to the state N plus 1. So I'm simply going to have, I'm going to look at this nth step. So I have P naught plus N delta P, but I can also just call this, P naught plus N minus 1 delta P, might be better, which I can just call P, and 1 minus P naught minus N minus 1 delta P, which I can just call 1 minus P. And this is going to change to P plus delta P and 1 minus P minus delta P. Okay, so delta ES I can see is 1 minus P minus delta P times ES. This is the final energy, minus 1 minus P ES, which is equal to minus delta P ES. So the change in energy of the system in a single step is given by this simple formula. Then I calculate the change in entropy of the system. And now what we're going to do is we're going to do this to first order. So we're going to say this is the rate of change of entropy with respect to population times delta P plus something that is order of delta P squared. And what is ds by dp? That is d over dp of minus p log p plus 1 minus p log 1 minus p. And this ds by dp is d by dp of this, which is minus 1 plus log p minus 1 minus log 1 minus p, which is minus log of p upon 1 minus p. Okay, now what we're going to use is that in the nth step, the Pn that I had was exactly derived from the thermal state of qubit Bn, which means that this is equal to minus log, and note that P upon 1 minus P is the inverse Gibbs ratio. It's the ground state divided by the excited state. So this is plus, the exponent e to the plus beta times EBN. Let me put it as Bn, is equal to minus beta times EBN. Okay, So what we get is delta S of the system is equal to minus beta delta P E Bn plus something that's order of delta P squared. Okay, so far so good. And finally, we look at the work cost. So we know that from just the conservation of energy or the accounting of the work, I have that the work that must be provided, so let's call this delta W, must be equal to the increase in energy of the system and the bath. So this must be equal to, so this is delta work that is inputted, is delta ES plus delta E of the bath. And delta E of the bath, how does delta E of the bath go? In the end step, the system increases by a small delta P. So the bath, of course, does the opposite thing. The system, the ground state increases by delta P. So the bath, the ground state must decrease by delta P. So this changes its state by a minus delta P. So the delta EB, therefore, is equal to plus delta P times E of the bath. So this is exactly the same way that we derived this here, delta ES from the final minus the initial. The same way we do it for the bath. The only difference is that delta P is now added to the ground state of the bath and subtracted from the excited state. So we end up with the plus delta P E of the bath N. Okay, and now we can combine all of this together. So we say delta W is equal to this. So this, we know delta ES is minus delta P ES and delta EB. So we have plus delta P EBN. But now I use what I just derived here for the change in entropy. Oh, sorry, this statement here to write this as minus delta P ES plus delta P, and EBN is now minus delta S over beta. And I can change, delta W is delta ES plus delta P. Oh, actually I didn't need to convert this. I can just keep this as delta ES. This is delta ES, and delta P times EBN is plus the change in entropy divided by beta. So I've used this equation over here. And this is clearly recognizable. This is now delta of ES minus SS, this is a system, over beta, which is equal to the change in the free energy of the system. So what I find is that in a single step of this operation, up to first order in the population change, the work that I had to input into this protocol is exactly equal to the change in free energy that I had, the change in free energy of the system with respect to, remember, the temperature of the bath. So this is the temperature of the bath that is involved. And the free energy is always defined with respect to that bath. So the increase in free energy is matched by the work that I have to put in. Okay, so what we get then is if we add up the total, so the total W that we get, so this, I could write this as order delta P squared. The total W that we get is equal to the delta F of the system, the total amount, adding up over all of the steps, plus I'm going to get something that is N times order of delta P squared. But N itself, like we can write, remember that delta P, P final was equal to P initial plus N delta P. So N and delta P are inversely related to one another. So I can write this as order of delta P inverse, in which case all of this becomes something that's of the order of delta P. which means that as I make my steps smaller and smaller, I end up getting something that is closer and closer to this ideal bound. That is simply the work that has to be inputted is the change in the free energy of my system. Now, the reason I did this with free energy instead of entropy is because this is a generalization. If I have that the Hamiltonian of the system is 0, then I would get that delta Fs is exactly equal to minus delta S of the system divided by beta, because there's no energy involved. And then I would get W total is equal to minus delta S over beta. And remember, this is a decrease in entropy. So we end up with our original, the delta S decreasing is equal to beta times W total, or which is the same as beta times Q into the bath, the dissipated heat into the bath. The reason I can say W is equal to Q is because there's no energy in the system. So via the first law of thermodynamics, whatever work was input must have been dissipated into the bath. And the point of saying this is to say that erasure is in fact actually a special example of cooling, because what we've done here is we've taken a system that actually had a Hamiltonian, had an energy gap, and we've pushed more and more population into its ground state. And this is something that's equivalent to erasure, except that in classical erasure, where you have a memory without any energy Hamiltonian, you don't look at the free energy, you only look at the entropy, because the free energy for no Hamiltonian simplifies into the entropy. But in fact, erasure is simply one facet of cooling in general. Okay, are there any questions about this? None so far. All right, very good. Pace of this lecture is quite good. So what I'm going to consider next is how do we write in explicit work sources. So this comes back to the question that was raised at the beginning of the lecture, because the manner in which I just did the erasure protocol right now, I didn't consider an explicit system that I use to store the work or extract the work. I simply considered that I could do any unitary I like, and I kept track of the work cost by looking at the difference in the average energy from the initial state to the final state. So the next thing to do, which is to make this protocol explicit, is to consider that I do keep track of where the work goes. I store the work into a particular system. So instead of saying, instead of allowing for arbitrary unitaries and then saying that W is equal to the trace of H rho final minus H rho initial, and H is here, H of the whole thing, the system and the bath, we now go to energy preserving unitaries. And these are U, system, and bath. But here we have U, system, bath, and weight. So we include the weight as a physical system. And then we say that W is equal to trace of H bath, rho bath, prime minus rho bath. And this is work stored increases. I can write this as W with the upper arrow. So I use the up and down arrow because every now and then when we have a final result, it's easier to write the result in terms of, sometimes in terms of work extracted, sometimes in terms of work stored, sometimes works of heat dissipated or heat extracted. And then we have to flip the signs of everything. So I use the up and down arrows to encode that information. Okay, so how would we then construct an explicit work source for the protocol we just had? So remember, a single step of our protocol involves the following. We had ES, we had EB, and we did the swap operation 0, 1, 1, 0. So the unitary was equal to 1, 0, 0, 1, 1, 0, which is equal to identity on the rest plus 0, 1, 1, 0, plus 1, 0, 0, 1. Now, this is not an energy preserving operation because 0, 1, and 1, 0 do not have the same energy. One of them has the energy ES, the other one has the energy EB. So the way to do it is to essentially involve another system. And now my work storage system, I'm going to introduce as an infinite ladder with a Hamiltonian which is continuous. So it simply has, let's call the Hamiltonian M, G, X, where X is the position on the ladder. So it's a continuous ladder, and its energy is given by the potential energy given how high you are on the ladder. And so what we can do now is we can take, this was our system USB, which was non-energy preserving, and we change it to an energy preserving unitary by simply doing the following. We say we have identity on the rest plus 0, 1, tensor 1, 0 on the system path tensored. Now, this is the system path part is one that takes the energy, it takes you from a state where you're excited on the system to one that's excited on the path, which is an increase in energy by EB minus ES. So we balance that by decreasing in energy EB, or translation of ES minus EB. And this is a translation operator on the weight, on the work storage, plus the Hermitian conjugate 1, 0, 0, 1, tensored EB minus ES. So what we've done here is we've balanced for every operation in this unitary, for every transformation of vectors. Oh, yes, the question?
May I ask about when you write identity rest, then
Yes.
you wrote USB and we have a 0 in the last position. So I'm a little bit confused. Is it a typo, or is it that identity rest is just for the beginning of the matrix?
Sorry, I didn't get, so in this, so the identity on the rest is different. In this case, the identity on the rest is the 0, 0, 0, 0 plus 1, 1, 1, 1, the states that are not involved in the unitary operation.
Okay.
Here I did, yes.
But then in the matrix that you wrote above, you have a 0 in 1, 1, 1, 1.
Oh, sorry. Yes. Yeah, that's a typo.
Oh,
That's,
okay. Okay.
Yes,
Perfect.
yes.
Perfect then.
Thanks. Yes, indeed.
Thank you very much.
Thanks for spotting that. Yes. So this is a unitary that now conserves energy. And when I say conserve energy, remember the conservation of energy is the following: USBW commutes with the following Hamiltonian: HS tensored identity on the path, tensored identity on the weight, plus identity on the system, tensor H path, tensor identity on the weight, plus this is the total Hamiltonian. Identity on the path, tensor H on the weight. And this is something very easy to check. It's pretty much by construction because we've ensured that every change, every state in the unitary is taken to another state that has the same total energy. This is equal to 0. Yeah, they commute. Okay, so right. So what we've done now is we've taken a protocol where the energy, the source of energy was not really explicitly included, and put it into the protocol. So we have now an explicit source of energy and energy preserving operations that ensure that the global state has the same energy as it started off with. So this is another way to sort of answer the question that was originally raised as to why we could have taken work as an observable which is what we did in the first time we did the Erasure protocol. And now we take work as a physical system that stores energy in its internal degree of freedom. Okay. Are there any questions so far? All right. If there are no questions, so what I will do is briefly go over again a derivation of the second law of thermodynamics in this case, which is the following. So I want to prove now, that we cannot extract work from heat. So imagine that I didn't have the system. So there's no system, just the bath and the weight. Okay, so I had the bath from which I can pick any Hamiltonian and any thermal state of that Hamiltonian, and I have my weight, and I do operations of this form. So of course my U bath weight is now going to be of the form identity on the rest plus 1, 0 on the bath minus EB plus 0, 1 on the bath, hence a translation of plus EB. So if the bath goes to a lower state, this goes to a higher state. If the bath goes to a higher state, the weight goes to a lower state. And then I consider, of course, a row bath, tensor row W, that goes to row prime. I keep writing S just out of habit, bath W. And now I want to consider whether I can actually do a unitary operation that takes heat from the bath and converts it to work. So I want to consider a unitary operation where delta E of the bath is less than 0, so that delta E of the weight is greater than 0. Remember that delta E of the bath plus delta E of the weight must be equal to 0 because we do energy preserving operations by the first law. But here's the reason that this doesn't work. And the reason is as follows. Delta E of the bath being less than 0, meaning that the energy of the state of the bath being less than 0, implies that delta S of the bath must also be less than 0. And the reason is the following. So remember from Jane's principle, what we derived, the thermal state is a state that for that energy, it maximizes the entropy. And the same thing goes the other way around. If we fix the entropy of a state, then the thermal state is the one that minimizes the energy given that entropy, which is the same thing as saying that the graph of, if we look at, if we fix the energy of a state, E average, and we look at the entropy, then this is the sort of graph that we get. And this is the maximum value of the graph. This is an upper bound. And that is satisfied by thermal states. So two things. One is that entropy increases monotonically with respect to energy for thermal states. And for every thermal state, it satisfies the property that for that energy, it has a maximal entropy, which means the following. Imagine we start with a thermal state. So we start with the state here. This is my row bath. And we know that we decrease the energy of the state. So we go somewhere to the left. So we go to some point on this line. This is delta E of the bath is less than 0, because we have started with this assumption. We've taken heat from the hot bath and put it into the weight. So we know that delta EB is less than 0, but because of the property that we have, we know therefore that all of the possible states, that is this line segment, have the property that the S of the bath prime is less than the original state. So this implies that delta S bath is also less than 0. And now we do something similar to what we did in Erasure. We have that S of rho prime S and bath is equal to S of rho S and bath. This is from unitarity. This in turn is equal to S of rho S. Oh, sorry, I said bath and weight, bath and weight, bath and weight, bath and weight, bath and weight. This is equal to the individual entropies, S of rho weight, and this is less or equal to rho S of rho bath prime plus S of rho W prime, which gives us that delta S of the bath plus delta S of the weight is greater or equal to 0. And this alone is less or equal to 0, or actually in our case, because of it's strictly monotonic, so delta SP is less than 0. And now here's the problem. So we were free to start with any state of the weight as we liked, which means that we can start with a state of the weight. So we have the weight, for example. We can start with a state of the weight that is mixed over a very large sort of span of the different height states of this ladder. So it's a maximally mixed distribution, maximally mixed over span, and let's call this span D, which means that the final state of the weight, remember that the weight rho B prime, the weight only changes by a translation upward or downward, depending on whether the system, sorry, not the system in this case, whether the bath goes from the ground state to the excited state, or the excited state to the ground state, which means that the weight, the final state of the weight, goes to a mixture of these two states, one of which is shifted up and one of which is shifted down, which means that the final state has a span that is at most D plus the energy of the bath, or 2 times the energy of the bath, because you could move up or you could move down. So in the case that you moved up or the case that you moved down, you would shift by EB, which means that whatever the initial span is, the maximal final span would be D plus 2 EB, which means that if my initial S of rho bath I choose by choosing it to be of that span to be log D, then my S of rho bath final is less or equal to log of D plus EB, which means that my delta S of bath is now less or equal to log of D plus EB upon D equal to log of 1 plus EB upon D, which can be arbitrarily close to 1. Oh, sorry, arbitrarily close to 0 by increasing D. And so now we have a problem. I can make delta S bath arbitrarily close to 0 by increasing the dimension of the span of the initial state of the weight. But by doing so, I will clearly get a contradiction here, because for any finite decrease in the entropy of the bath, I can just choose a state of the weight such that that delta S is, oops, sorry, again, I've made a mistake here. These are all weight. Weight. I apologize. I can always choose a state of the weight such that this delta S is less, and then I will have that the sum is going to be less than 0 because delta SB is less than 0, and that's a contradiction. The only way I get no contradiction is if it's not allowed for delta S of the bath to be less than 0, but the only way that can be the case is if delta EB is not allowed to be less than 0, which means that I cannot apply any unitary operation that satisfies these conditions in which I extract heat and I convert it into work. And so I get now another form of the second law with an explicit work source. Is there any question about this? I've mixed up notations a number of times, so if there's an uncertainty, please ask.
Might have one regarding why this now gives a contradiction in the general case. and not just for the case where we have a large work storage system, because we needed to increase the dimensionality of our work storage system to contradict this inequality. Why doesn't this, or does this also imply for a small work storage system that we cannot extract work from a bath, or is it just for macroscopically large systems?
Yes, that's a very good question. So the reasoning is as follows. So it is definitely true that if I allowed myself to do any unitary operation on the bath and the weight, or in more generally on the system bath and weight, then I could use the change in entropy of the bath to actually end up extracting heat and putting it into the bath. And the way that would work is because I ended up increasing the entropy of the bath, and so I don't get a contradiction from the second law. Now, there are two ingredients to this proof. The first ingredient is that the unitaries that I allow myself to do are only of this form. So they are only of the form that are translationally invariant on the bath. So this is to say that the operation that I do does not, it has two properties. One is that it's translationally invariant, regardless of where the bath starts. All that it does is a translation operation depending on the energy of the other, translationally invariant on the weight. I don't know why I keep saying bath. Transitionally invariant on the weight the work storage system. Yes, so the only way the work storage system changes is via an energy change in the system and the bath that's attached to it. And the second property that this operation satisfies, is that it does not depend on the initial state of the weight. So the change in the entropy of the bath and the change in the energy of the bath is independent of the initial state of the weight if we do an operation like this. Because this operation, which only has translations, clearly doesn't care where the weight starts off it. It just pushes it up or down, regardless of where it starts off with. So the reduced state of the bath that we see at the end, or the reduced state of the system and the bath that we see at the end, is independent of what state of the weight we pick in the initial condition. And so all of this argument now, the way it follows is the following. If given that my end state of the bath is independent of my initial state of the weight, whatever my end state of the bath is, it should be the same regardless of what state of the weight I pick. Now, we know that if my end state of the bath is one that it's decreased in energy, then I know that the entropy of the bath has decreased, which gives us, well, so I get this statement. So I start with the assumption that I did some operation, my final state of the bath has less energy, so my final state of the bath has less entropy. But this is independent of what initial state I picked on the weight, because the operations that I'm allowed to do are only those that are translationally invariant and do not depend on the initial state of the weight. Therefore, I can pick whatever state of the weight I like, and these two statements should still hold true. However, if I do pick a state of the weight that does as much support as I like, then I will get a contradiction, which means that the only manner in which I can proceed is when these two statements, or rather this statement that the bath has decreased in energy, is not true. So I get a contradiction by using the fact that I can pick any initial state of the weight, given that the operations I'm allowed to do are translation invariant. Does this answer the question?
Yes, absolutely. Thanks a lot.
Thank you very much for the question, because it's indeed, I should have started by saying this. When I introduce a work storage system, it's important to choose the operations that you do on the system, the bath, and the work storage system to be of the form that they don't use particular information you might have about where the work storage system is. So the operations that you choose should be ones that do not depend on the initial state of the weight. And this class of operations that are translation invariant have both the properties that they are energy conserving and they do not depend on the initial state of the weight. Okay. Any other question on this? If not, then I will proceed to so I have two options on how to finish the lecture. Okay, so I will do the following. So there are two things I would like to do now. One is the quantum sort of negative information erasure, and the other is considering a hot path. But okay, so let me do. In fact, let me do the other one first. So a source of heat rather than work. So far, when we've considered both erasure as well as here the explicit protocol, the theoretical bound as well as the explicit protocol, we consider there to be a single environment temperature that we had access to, and that our source of work was idealized. So it was a source on which we could assume that the entropy of the work source didn't change by much, or didn't, well, change by an arbitrarily small amount or zero. Instead, let's consider that we actually do not have an idealized source of work, but in fact, we have to use another thermal bath as a source of work. So now our setting is the following. We have TR, or let's say, or beta R, which is our environment reservoir. And the other is a T hot, which is a hot bath. So beta hot is less than beta cold, which is the same as saying T hot is greater than T cold. Okay, and rather than have to use a work source, we're going to use the hot bath as a source. So what we do now is we consider the same erasure protocol. So we had an ES, which started with P naught and 1 minus P naught. And then we swapped it with a sequence of states from the bath with the property that the first one of them starts with a delta P, 1 minus P naught minus delta P, and then so on and so forth with 2 delta P, 3 delta P, etc. And so the single step in this protocol is of this form. I have an ES, I have an EB, and I want to swap these two states. Now, we do exactly the same thing as we did in the case of the work extraction, as in the case of the work storage, where we introduced a Hamiltonian that allowed us to pick translation operators that plug the gap. Here, what we're going to do is we're going to simply pick a Hamiltonian of the difference in the energy gap. So this starts out at e to the minus beta h path, and this is going to start off, and this is going to be beta, let me call this room for reservoir, and this is going to start off at e to the minus beta hot h of the hot path. Actually, let me now label the reservoir also by R, because this will be convenient, by Z. So in other words, instead of plugging the degeneracy by using a ladder, we plug the degeneracy by using a single qubit that is exactly of the same energy gap as between the system and the bath. So now, when we do 0, 1, 1, 0 between the system and bath, we can tensor this with, if the system goes down in energy, we want the bath to go down in energy as well. Hot plus 1, 0, 0, 1, tensor 1, 0, hot, plus, as usual, identity on the rest. And this I can write actually in a nicer form, 0, 1, 0, 1, 0, 1 on SPH plus the Hermitian conjugate plus identity on the rest. And that is the following transition. The bath and the hot qubit lose energy. Sorry, the system and the hot qubit lose energy. And the room temperature qubit, the room temperature reservoir, gains energy. So this is clearly by construction also an energy preserving unitary because USPH is going to commute with HS plus HR plus HB. I'm not going to write them out in full. Each of these is, of course, identity on everything else, tensored H of that particular system. Okay, so by doing this, we are able now to mimic the previous protocol. Instead of doing the swap between the system and bath and a work storage ladder, we're now doing the swap between the system and bath and a hot qubit. But there is one important difference here, which is the following. In the original two cases, so in the case of implicit work or ideal work storage, we had rho system prime was equal to rho bath. What this means is that the swap operation led to the two populations, the populations of the system and the bath completely swapping, because 0, 1 went to 0, 1, 0, and vice versa. In this case here, this is no longer true. And the reason is because this operation here, 0, 1, 0, 1, 0, 1, does not completely swap the system and the bath. It only swaps the system and the bath in the subspace in which the hot qubit lies. And another way of looking at this is, in order to swap the system and the bath entirely, you would need 0, 1. Well, okay, let's not write it in this fashion. Let's actually compute it explicitly. So let's look at, if I consider that the system starts with P 1 minus P, and my bath is in Q 1 minus Q, my reservoir. So this is the reservoir, and the hot bath is in R 1 minus R. Then what I have from swapping these two states, remember the populations of these two states are, so 0, 1, 0 as a population of P times 1 minus Q times R, and 1, 0, 1 has a population of 1 minus P times Q times 1 minus R. And so when I switch these two populations around, what I get is that P goes to what it used to be before, and now it increases by this amount here. So it goes to 1 minus P times Q times 1 minus R, and it decreases by the amount P 1 minus Q times R. Yes, so this is now with a hot bath involved. But remember, with the original swap, so the original ideal swap was that P went to P plus, and there was no R and 1 minus R. We simply were able to swap these two populations completely, 1 minus Q, and this is equal to, well, let me check, but it should be correct, minus PQ minus P plus PQ, which is equal to Q. So P completely swapped to Q. Whereas in this case here, in the non-ideal case, we get something in between P and Q. And this is something very similar. I'm not going to do the calculation here, but if we did this calculation, we would find it very similar to the calculation that we did when we wrote about a real qubit swapping with a virtual qubit. And the result there was that when a real qubit swaps with a virtual qubit, we don't go completely to the population we would have expected if it was swapping with a real qubit, but something in between. And because we've involved the hot qubit now, and we are swapping not only on the system and bath, but on the system and the original reservoir bath as well as a hot bath, we don't completely end up swapping the system to the populations of the bath, but in fact, we end up swapping to something in between. And this is something you will explore further in a tutorial question. And the result is that in order to fully mimic the protocol that we just considered, the Erasure protocol, we cannot simply do a single swap between system reservoir and the hot bath, and then proceed to the next stage where we consider a slightly larger energy gap in the reservoir. But in fact, we have to repeat the operation a number of times to get close to the asymptotic state that we would get, following the same logic as real qubit swapping with virtual qubits. We have to repeat it a number of times to get close to that state, and then proceed to the next stage. So each of these stages here is now split into a number of steps, where each step involves swapping the state of the system with that of the reservoir and the hot bath, rethermalizing the reservoir to its temperature, the hot bath to its temperature, repeating that swap again, so that the system then eventually tends to the virtual qubit that it's supposed to via repeated operations. Another important difference when we swap involving a hot bath is that the virtual temperature that the system tends to is in fact not the one that's given only by the room temperature bath, but now by the room temperature and the hot bath. So if we were to write the Gibbs ratios of the system, so we have now, let me draw this again. This is my system. Oh, sorry. This is my bath, and this is the hot qubit. If we had no hot bath and an idealized swap, the Gibbs ratio that we see, so the system sort of swaps with a Gibbs ratio of e to the minus EB times beta of the room temperature. This is EB, and this is EB minus ES. So when we swap the system with only the bath, and it's an idealized swap, there's no need of a hot bath, or the work storage system is implicit, then the system sees the Gibbs ratio of e to the minus beta R EB, and that's the ratio that it goes to itself when you do a single swap. But if you have a hot bath, then what the system sees now is not in fact just the bath, but it sees the joint state. So we have the system here, and we have the joint state of the reservoir. Oh, I call this bath, but let me call this reservoir, as well as the hot. And this is now energy 0. This is at energy EB minus ES. This is at energy EB, and this is at energy 2 EB minus ES. So I've just added up the energies. So this is 0 EB, 0 EB minus ES to form the total Hamiltonian. And clearly the swap that we're doing, which is the 0, 1, 0, 1, 0, 1 swap, is this one. This goes up. Sorry, this goes down, this goes up, this goes up, this goes down. So the way to describe it when we have a hot bath is that the system, rather than swapping with the real qubit, which is just the bath qubit, instead swaps with the virtual qubit that has been formed by the juxtaposition of the original bath and the hot bath. And that immediately tells you, first of all, what we just discussed, that in a single operation, a single swap operation, you're not going to go to the same Gibbs ratio as you see in the virtual qubit. You need to repeat the operation a number of times to get there. But the second thing it says is that the Gibbs ratio that we see on the virtual qubit is not the original one, because this Gibbs ratio now is going to be, so this is the state 1, 0, and this is the state 0, 1. So the Gibbs ratio is going to be e to the minus beta R EB. That comes from the ratio on the bath times e to the plus beta hot EB minus ES. So the Gibbs ratio of the virtual qubit is equal to e to the minus beta R EB plus beta hot EB minus ES. And this is clearly greater or equal to, well, greater than, there's no equal to, e to the minus beta R EB. because the term that we've added in the exponential is positive. EB is greater than ES. Beta hot is, beta hot is a positive hot temperature. And so what this implies is that when we consider that our work source is in fact not for free, but we have to generate it from a hot path, two things change. One is that the number of operations that we have to do in order to do the original erasure protocol increases, because a single swap operation in each stage is not enough to take us to the temperature or the Gibbs ratio that we are expecting to get from that stage. And the second thing that we get is that that final Gibbs ratio that we get in that stage is also slightly worse, slightly hotter than the Gibbs ratio we had in the original protocol, which means that we would have to continue this operation. We would have to add more stages to get the Gibbs ratio at the end that we would like to. And that end Gibbs ratio is determined by how erased we want the state of the system to be. So this basically implies that when we take away the implicitness of the work storage systems and we include it explicitly as a hot path with energy preserving operations that have to obey the first law, we end up with the possibility of getting different results, specifically that cooling and erasure takes greater amount of time and is not as good as that we get with implicit work storages included for free. Are there any questions about this? None whatsoever? Okay. In that case, I think, well, since there are only 3 minutes to the official time, I think we can wrap up the lecture for this week. I have an announcement to make. I don't yet have, well, actually, let me. So there is one announcement that I've been asked to make, which is that there is a survey, a student satisfaction survey that is being passed around to all students. And we've been asked to remind you to please fill in that survey because it's important for well, future lectures and future plans, especially during these times of COVID, where a lot of adjustments are made. So please fill in that survey when it gets sent to you. Yes. And with that announcement, I think I will wrap up the lecture and say, see you all in 2 weeks' time. Have a very nice and relaxed Easter break. Thank you very much.